Hello everyone, I am Jasna Kemerson. I would like to explain Floyd Warshall Algorithm, which is used to find all-pair shortest path problem from a weighted. It is also known in different names: Floyd's algorithm, Floyd's algorithm, Roy Warshall algorithm, or WFI algorithm. This algorithm follows a dynamic programming approach to find the shortest path. The Floyd Warshall algorithm was first published by Robert Floyd and Stephen Warshall in 1962, and this algorithm's original goal was to address the transitive closure problem, which asks if a path connects every pair of vertices in a directed network. And the approach updates a matrix, and these matrices represents the shortest path between each pair of vertices iteratively, and the algorithm was later generalized to solve the all-pair shortest path problem, which involves finding the shortest path between every pair of vertices in a weighted directed path. So, the Floyd Warshall algorithm, which is used to find all pairs shortest paths in a weighted graph, it is computing the shortest path between every pair of vertices in the graph. Now let's see the algorithm. Algorithm works by repeatedly updating a matrix that represents the shortest path between each pair of vertices. So the steps are: initially we represent a matrix T, say that D represents the value of the matrix is the weight of the edges in the graph, and if there is no edges between two vertices, then the weight should be set as infinity, and if not, the values have been represented. And the iterate through each vertex in the graph. Let's call this vertex k. Suppose we take for each k a k is equal to 1, the vertex 1, k is equal to 2, k is equal to 3, and k is equal to 4 in this case. And for each pair of vertices I comma j, update the values of di comma j to be the minimum of the current value of current value of di comma j and the sum of the values of di comma k and dk comma j. In this case, we initially consider d0 and then we compute d1 on the basis of this condition. And after iterating through all the vertices of k, so k is equal to 1 for k, we consider k is equal to 1, and then we keep the rows and columns of k to be constant, and we compute the rest of them. And then for k is equal to 2 we compute, in which we've been completed d1. So we take that to be the matrix 1 d1, and then we keep the values of k is equal to 2 rows and columns to be similar, be constant in d1, and then we compute for d2. And then in d2 what we do in d2 we take k is equal to 3. In this case we keep the values of k is equal to 3 in d2 to be constant, and then we compute, and then the similar way we repeat for d4 and d5 if the vertices are till d5, or if the vertices are there. And now we'll be explaining through a graph, through an example. So in this graph we see that there are vertex number 4 n is equal to 4, and now the edges are from 1 to 2, 1 to 3, and then 1, and the vertex, there is no edges from 1 to 4 in direct. So we need to find the shortest path from 1 to 4. So on computing this, we will be considering d0, which we mentioned in the above slide, that we'll be considering d0 to be the initial matrix in which all the values of the matrix represents the weight of the edge. So here 1 to 1 there is no loop, so it is represented as dash, and 1 to 2, see 1 to 2 the value is 3, so we represent it as 3. And now 1 to 3, what is 1 to 3? 2, and there is no 1 to 4, which represents infinity. In similar way we go for 2 to 1, 2 to 1, 3, and 2 to 2, no loop, and then 2 to 3, 1 is the weight, and 2 to 4, 4 is the value. Similarly from 3 to 1, 2 is the value, and 3 to 2, 1 is the value, there is no loop, and then 3 to 4, 3 is the value. Similarly we write for 4, from 4 to 1 there is no path indirect, so we represented that as infinity. And then 4 to 2 the weight is 4, 4 to 3 the weight is 3, and 4 to 4, since there is no loop, this is the condition. So this is the initial matrix we get. And now D1 matrix is needed to be created by using D0 matrix. We keep D0 matrix, and here we will consider an intermediate value, like we say in the above slide, k is equal to 1. We consider k is equal to 1 to be constant. So we will take a better shortest, we will get a better shortest path going through vertex 1. So now D0 is the first matrix. D0 is the matrix we computed by the weight of the graph, and then D1 has to be computed. What we do? We consider k is equal to 1 and the pivot row and the pivot column to be constant. So the values of D0 is exactly repeated in the D1, in which for k is equal to 1, these both seems similar, like they are kept constant. Now we need to compute D2, 3, D0 of 2, 4, D0 of 3, 2, D0 of 3, 4, and D0 of 4, 2, D0 of 3, 4. So these are the values to be computed, and since this is an undirected graph, we say that D0 of 2, 3 and D0 of 3, 2 are equal. So now we compute this. Since the vertex has no loop, the diagonal values will be 0, or they are represented by dash. We can say it as 0. So now we are computing as the algorithm will take D0 of 2, 3. What is it? 1. And then we compute D0 of keeping I, j rise to, and k is 1. And then j, k. Here 2, 3. So I is equal to 2 and j is equal to 3. Now 1, 3. So D0 of 2, 1. What is 2, 1? 3. And then what is 1, 3? 1, 3 is 2. So on calculating, we get 2 plus 3, 2 plus 3, that is 5. So 1 is lesser. So we place here 1. So that is where we will be placing the value to be 1. We will keep here 1. That is, we are going to write here 1. Similarly, since it is an undirected graph, we can say that 2, 3 and 2, 3 and 3, 2 are similar. So we give here 1. So now in the similar way, what we will do? To D0 of 2, 4. This is the next value which we have to compute. So D0 of 2, 4 in the above matrix was 4. And now we compute through 2, 1. Now this is founded in the way that in the graph we will find the value of 2, 1 and then 1, 4. So 1, 4 is infinity. So adding a finite value to infinity again give an infinite value. So we represent it by infinity. So again this is infinity. So infinity, and what is the above metric value? 4. So what is the we were telling that in the algorithm minimum values being taken. So minimum of infinity, 4 we will write here as 4. So similarly, since it is an undirected graph, we write here also 4. The similar way we will be computing 3, 4, D0 of D1 of 3, 4. So we will be comparing D0 of 3, 4 is equal to 3 in the above matrix, and then we will be seeing D0 of 3, 1 is what? 2, and then D0 of 1, 4. What's 1, 4? Infinity. So adding an infinite value to infinite value again gives an infinity. So 3, infinity. What is the minimum? 3. So we replace here 3 and here also 3. So we get the D1 matrix. This is how we do the algorithm. So now we find that. So now we get D1. For k is equal to 1, we have found D1, the D1 matrix, and now we need to find D2 matrix. For k is equal to 2, as we keep the rows and the column of 2 to be constant, and we'll be computing D1. We will be comparing and finding the values of D2 of 1, 3, D2 of 1, 4, and D2 of 3, 4. So in here we see that the rest of the remains the same, but here D2, if we pass through 2, if we have an edge through 2, like 1, 4 is infinity. We know that because it doesn't have an edge between them. But if we go through 2, D1, d1 of 1 comma 2 is 3 and d1 of 2 comma 4 is 4. So 3 plus 4 is 7 and d1 of 1 comma 4 is infinity. So minimum of infinity comma 7 we get 7. So we will be placing d2 of 1 comma 4 and d2 of 4 comma 1 to be 7. So we will get we will be replacing the values to be this. So that's how we find for k is equal to 2. We will be again computing for each values. We will be seeing whether there is any changes and then we will be finding that for k is equal to 2 also we will be finding. Similarly, we will be computing for k is equal to 3, keeping 3 as the pivot row and column, and then we will be computing and we will get the matrix this. In this we see that in the above matrix it was 7 here, which means from 1 to 4 to 2 through 2 it was 7, which means from 1 to 2, 2 to 4 the value is 7. 3 plus 4 that was 7. So now we are keeping 3 as the pivot row and column. So we'll be going, the vertex will be, we will find a path through 3. So 1 to 3, what is this? 2. And 3 to 4, what is this? 3. So 2 plus 3, that is 5. So from 1 to 4, that was infinity. The minimum of infinity comma 5, we get that 5 is the minimum value. So so we get that these values are being changed. So the minimum of in each step we will be finding the optimal value. So through which vertex if we go, we'll get the shortest path. That is what we are finding. So now if we go through 3, we get the shortest path from 1 to 4. So that's what we received here, and then we keep the next vertex for k is equal to 4. We keep the vertex k to be constant and then we will be computing. On this we will see that no changes are being occurred since from vertex 4 all are optimal because from D3 as we move from D3 we through D3 we find this is the optimal not the shortest path, which is we will find the shortest path through each vertex. So this is how we find, and so we get that D4, and then we'll be seeing the summary. So on seeing the summary, we'll be seeing that before applying the algorithm d1 comma 2 and that means distance between 1 comma 2 and distance between 2 comma 1 was 3, and after applying the algorithm was also 3, which means that the given graph shows the shortest distance. And similarly d1 comma 3 and d3 comma 1 is equal to 2, and for after applying the algorithm this remains same, but see for 1 comma 4 and d4 comma 1 this is infinity, which sees, and after applying the algorithm d1 comma 4 and d4 comma 1 is 5, where the as we found that when we pass from when we pass the vertex, when we find a path from 1 to 3 and 3 to 4, we find the shortest path. So we replace the infinity by the shortest value, which is 5, because in the algorithm we are finding the shortest path through from every pair of vertices, and then we find that d2 comma 3 and 3 comma 2 is equal to 1, similar after applying, and so we find that we have replaced the infinity by a particular value, which means we have find the shortest path between each pair of vertices. So the advantage of this algorithm is we can solve a wide range of problems, calculating the transitive closure of a graph and dictating the negative cycles in the graph. These are the advantages of applying this algorithm. And this is all about Floyd Warshall algorithm. Thank you for listening. Thank you.